Everybody, we're going to start scientific method notes today, probably finish them tomorrow. So really we're going to look at what is considered sometimes a linear process really is a circular process, because most of the time in science it doesn't work exactly the way we think it is. In science you've done lots of experiments and you will continue to, and they all work because we know they work. But in real science, it doesn't always work the first time or the 20th time. And a lot of times as we, refine our experiments, we come to more questions at the end that helps us decide how to change the experiment for the next time, so that maybe by processing out things that don't work, we figure out why it works. And Einstein said the difference between stupidity and genius is that genius has its limits. But what I think that means is that when we stop questioning, we stop learning. And the scientific method is a way to systematically figure out how things work. So that's what we're going to be talking about today. But first, we have to get into what is science. Well, it's a systematic study of nature and the behavior of the universe. It's based on observation, experimentations, and measurement. It discovers theories and laws that describe the facts in general terms. Now, we still say the law of gravity, and we still say the theory of relativity. Most scientists today don't really call much of anything a law anymore because we're always refining it. Even Newton's three laws of motion, inertia and action, reaction, all of those, force equals mass times acceleration, he came up with them, but they were actually tweaked over the years. We refined them, we made them better. So in science, you're going to have opinions, beliefs, emotions, all those human failings. And that's true. But in science, you've got to kind of go past that, because when you're doing a scientific experiment, you're actually not allowed to have opinions, beliefs, and emotions, because I can be really passionate that what I think I'm doing is right. But if the data is telling me it's wrong, then I have to accept the data and try and figure out how to make it better. So we have to be careful of those opinions and beliefs and emotions, because we can become passionate about it. But in a scientist, you have to be able to let go and adapt and move on to new ways. So that's kind of what science is all about. So science can only have a testable hypothesis. In other words, it needs to be a question that I can say that you are the coolest person in the world, and I might be able to even come up with an experiment to figure that out. But I can't say definitively that, let's say, Milky Way is the best candy bar in the world, because everyone's taste buds are different. I could say statistically what the preference is for that candy bar over, say, a Snickers or a Reese's Peanut Butter Cup, which would actually be my choice, but that's a different issue. Um, there are questions that are testable and there are questions that are opinion based, and we go for testable. And it needs to be repeatable. And science bases its laws and theories on that evidence. And the cool thing is, so much information flows so fast in our society that we're making leaps and bounds. But if you were, say, Copernicus or Galileo or Curie or Einstein, you were really basing your work on, if you were them at that time, on what you could get your hands on for what had been disseminated, what had been distributed. And they based their foundation on the work that had come before them. Newton used some of the work of Galileo, who used some of the work of Copernicus. And all of this came about because they had previous knowledge. Then you get into Tesla, who came up with, alternating current for electricity, the stuff we use today in our households. When you were looking at the race for DC versus AC, we had somebody advocating really hard for DC, but AC is the one that won out. But he used the information from all the people before him. Einstein used all the information from the people that came before him to come up with this theory of relativity. And we've now, as scientists, based all of our findings on having that foundational knowledge that took a long time to amass. But because information flows so freely through the internet, we can publish so much faster. we have the ability to go through and learn and build faster and faster. And our science knowledge is growing in leaps and bounds. What used to take hundreds of years can sometimes take months. But we also have to be careful when we go on Google, because you can have information that is incorrect. You have to watch your sources. A study that comes out that says bacon is the best thing ever for you, and then the next one comes out and says the worst thing ever for you, and the next one comes out and said you've got to eat bacon all the time. Well, you have to look at the study. Has it been peer reviewed? Has it been has somebody else been able to reproduce those results? Because if it hasn't been peer reviewed, that's not good scientific reasoning. We did a research science project in ninth grade, and everyone had to look to figure. Actually, it was eighth grade, and I asked them, when did we have volcanoes in Minnesota? And it was on a test, and I'd give them, they could Google it. The problem was they Googled it off of someone's information that was wrong, but it came up in a Google box. I mean, it was right there, the very first thing they saw, and they said it happened 18 million years ago, and that it cost $45 billion in damages. No, it's $1.2 billion in damages, and 45 people died. Well, we had to stop and talk about that because, for one thing, modern humans have been around for 100, 200,000 years. You couldn't have had 45 people die 18 million years ago. We just simply weren't here. And you wouldn't have had, $1.2 billion in damages 18 million years ago because there wasn't money. So you have to be careful of that. By the way, the answer is about 1.1, 1.2, 1.3 billion years ago, we had volcanoes in Minnesota in the Duluth area. So they didn't get the right answer, but it became a learning opportunity because we had to explain why you needed to look that information and use the stuff you already know to figure out if that's credible. And credible science has been peer reviewed. That is, it has been published. Someone else has taken it, tried to recreate using the same exact methodology, and came up with the same results. Without that peer review, it is not a good scientific publication. But we build all of our science knowledge on those that came before us. So Madame Curie, or Nikola Tesla, or Copernicus, or Galileo, or Newton, or Einstein, all these people, Meitzer, all these people give us the foundation of where we are today. So if you are in the regular notes, and we're going through this in class, then you're going to be answering these questions. Why do scientists conduct an experiment? And what should they do to avoid an experiment? If you're watching this on Edpuzzle, you're going to answer the same question, but digitally. Okay, so scientific method, we're going to go through it. Remember, I said it shows linear, but it's really circular. And that's a big thing to understand, because in it, we have to state our problem. So what's our question? What are we wondering about? Then we need to do some background research on it. And from that little bit, we're going to form a hypothesis. And now this hypothesis is something that needs to be testable. So it's a question stated kind of in an if, then, because way. If this happens, then this should happen because of this. So if, then, because. So we form that hypothesis. Once we form a hypothesis, what do we want to test? Then we have to design the experiment. Once we've designed it, then we need to actually conduct the experiment. And then once it's done, we need to take all of that data that we gathered and analyze the information, and then state the conclusion. And sometimes that stating the conclusion is publishing. But if you're Sheldon, we're going to go to the bigger one. You just speak it. So here we go. Here's scientific method. And just to make sure I've got this okay, I'm going to turn the volume up. And it would help if I use the correct remote. Here we go.
Have you noticed that Howard can take any topic and use it to remind you that he went to space?
Interesting hypothesis. Let's apply the scientific method. Perform an experiment.
Okay. Hey, Howard, any thoughts on where we should get dinner?
Anywhere but the space station. I mean, on a good day, dinner was a bag full of meatloaf. But hey, you don't go there for the food, you go there for the view.
Okay, so now they're going to repeat it.
Fascinating. Let me see if I can duplicate the result.
Howard,
I've always thought the lemon was an underrated fruit. Care to weigh in?
Not really.
Oh, well.
You know, people say the Soyuz capsule is a lemon, but... Yeah, but hey, that baby got me to space and back.
Okay, so that is a testable, repeatable. They formed a hypothesis, they created the test, which was ask the question, and they performed it, and then they did it again and found out that they get the same result. So we're going to go through just kind of the fundamentals. What are the different parts of it? And then at some point here, we're going to stop briefly and do a walk the plank quiz, which you get to try and sync the teacher and send them to the sharks. And that is a link that we'll be doing on the assignment right below this one. So stating the problem, we talked about this. This is just a quick repeat. And this is also, you'll notice this dark wording here, or a slightly different color. It's almost a reddish. This is examples of an experiment that we're going to kind of run through as we're talking through the different parts. So if I state the problem, it should state the effect of the independent variable on the dependent variable. And in the independent variable, ladies and gentlemen, is the one we change. What am I going to manipulate? The dependent variable is the responding variable. It's the one that changes because I changed the other thing. So we're going to gather our evidence. We're going to do, I mean, this is old school. We're going to get out books and encyclopedias. In your generation, you would get on your phone. But then again, of course, you have to be careful of your sources. So we're going to find out as much background material as possible. You can use the internet or old, books. But usually the internet is more up to date. Then we're going to come up with our hypothesis. And a hypothesis is not actually a guess. It explains some observed facts. It's a proposed explanation made on limited evidence as a starting point of an investigation. That's important. It's a starting point. Doesn't mean you're going to get the final result at the end. You may have to do this again and again to get to the final one. It is a tentative or trial solution to a question. It guides the investigation. It's telling us which direction to go. You will create a good question in your experiment, that if-then statement. Then I also want a because. If-then, because this is going to happen. So a question that is testable with materials based at hand. So let's say I have a balsa wood glider airplane. You guys know what those look like. Hopefully, maybe I'm dating myself, but if not, there's a picture coming up. So let's say here's my hypothesis. If the length of the increases, then the time of descent will increase. Now, I would like this better. This is one I actually borrowed from the internet, and I cite my source a little later. I would actually like the because in there. If the length of the wing increases, then the descent of time will increase due to increased surface area holding it aloft longer, is my hypothesis. It is a testable, repeatable event. And then at the end, we determine, was that testable, repeatable hypothesis right or wrong, or do I need to modify? Then I'm going to design the experiment. So here's our experiment. Don't forget to create a title. That's important. We need to know what, experiment we're doing. So the effective wing length on the length of the time it takes a plane to land is my title. So here are some of the parameters of my experiment. How many trials? These are the things I need to figure out and put into my information. How many trials should we do? How many different lengths of wings are we going to test? How many trials should be done at each length? What height should the plane be started at for descent? What should the constant speed of the plane be before it descends? What tools will be used to measure the landing distance? All of these things are things I need to think about ahead of time and come up with the actual, how many times are we going to do this? How many different, lengths of wings are we going to test? We talked about this a second ago. These are on the test. You need to understand the difference between an independent variable, which is the one you manipulate. You purposely change it. So independent variable, I was actually taught it called the manipulated variable. I kind of like manipulated variable better because it says to me exactly what it is. I'm manipulating this. I'm changing this. But the book and most of science uses independent variables. So I put them both together to help you remember that the independent variable is the one you manipulate. In this case, what is the airplane's independent variable? It's the length of the wing in centimeters. because remember, we're science. We don't actually use those 4-letter words like foot, inch, yard, mile. We use centimeters and meters and millimeters and kilometers and kilograms and milligrams and milliliters and kiloliters. We use metric because that's what the rest of the world uses. So if you want to be able to share your results, you need to be in the measurement system the rest of the world uses. Otherwise, you have problems like we did years and years before you were born, where we had a mission landing on Mars to deploy a rover, and it's a combination between the European Space Agency and NASA. And when we brought some of their calculations over, our people forgot to convert it into US standard, inches, meters, miles. And that, millions of dollar and massive amounts of time endeavor failed because it had crashed into the planet and not deployed its parachutes because it thought it was still up in the atmosphere because of a math error. So we have to be very careful with that. We use metric in science. So the dependent variable then is what responds to the manipulation, the independent variable. So the dependent variable depends on what happened in the independent one. It changes because of your choices earlier. In this case, the length of the wing or the time in descent, all of those things. So which one are we changing? Well, we're changing probably the length of the wing. What do we think is going to be dependent on that manipulation? The time it stays in the air in seconds. So the change is your choice earlier, and we respond to this. So the dependent variable is the responding variable. So what's the descent variable? In this case, time of descent measured in seconds. I'm not going to show this to you. They are in the notes. By the way, these notes, if you're watching this, and I'm not doing this live with you, that means that you can go back into the notes at any time. You don't have to watch the video again. I always have a hard copy of the notes available. But this is a science teacher who is more talented musically than I am. And I am probably never going to sing for you because you just don't want that. But he came up with a song that kind of reinforces independent and dependent variables, manipulated and responding variables. And if that's how you learn better, here is a resource you can go back and do to watch it. This guy is good, but he screams. Again, it's one that you can go back and review. If I am not here, you don't want to watch the video and have me explain it to you, go back and watch it in those, and they're embedded in the notes. There is a third variable we haven't talked about yet, and that's the controlled variable. And it's what stays constant during the experiment, what you compare your results to. And we want really, as much as we can, to simply change one thing at a time. You never want to have multiple variables. They're called confounding variables because they can really, if you're experimenting on more than one change at a time, I don't know the reason why it changed then. It could be because of this one, or it could be because of that one, or as a combination of the two. So whenever possible, we try and avoid confounding variables, and we just go with one variable. Everything else is controlled. It stays the same. It's what I compare it to. So this is the unchanged part of the experiment that detects the effects of the hidden variables. So in this case, what do we want to have constant? Well, we want to always have the same structure of the airplane. We want to have the same dropping technique. We want to have the same dropping height. We want to control the beginning length of the wing at 5 centimeters. We're going to compare everything to that. When you're doing an experiment, it's really important that if you're not using electronic timers, that you always have the same person timing every time, because we all have this thing called a reaction time. And if you have different timers, then you can have a confounding variable of you had an error in timing. Now, we also will do some experiments if we're using stopwatches where we might have 4 of you running your stopwatch at the same exact time to help mitigate some of that, and then take the average of all 4 unless there's an outlier. That's another way to control that. But you always want, as much as you can, to have the same dropping techniques, the same. So in other words, you want the same person launching so that they have the same force of throw, that they're dropping from the same height, that they're going at the same angle, that the timers are the same. So as much as you can keep the same, you need to do that to have a valid experiment. And we're going to base everything off as we change our wing height, our wing length, to how it compared to that original one at 5 centimeters. So our control is what we don't manipulate, what we're trying to keep constant throughout the whole thing. Now we need to get actually into the experiment. Many trials are always better than one. They need to be clearly labeled. We need to record our observations. We need to create data tables to put that data in. So qualitative observations versus quantitative observations. A qualitative observation is as we land the plane, we observe that they were affected by air currents, which is a possible error. It appears that the longer wingspan took longer to reach the ground. These are qualitative observations. They're what we observe. Quantitative is quantity or data. This is where we actually use our data tables. So we're recording the time. We're recording that. So here in this case, we did 5 trials. We did 5 different lengths of the wing, but we did multiple trials of each length. And you'll notice that they weren't all exactly the same. So that's why we want multiple. If they'd done 20 drops, it actually probably would have been better. But then what we do is we take the average. So as the wing length increased, you'll notice that their average time also increased, but not necessarily in each individual trial. 3, 5, 4 averages to 4, 4, 5, 6 average to 5. And sometimes you could have all of them the same. It just depends. And then we can take this data and we can, when we get into analysis, we can actually graph it and see that as the length of the wing increased, our time increased. By the way, if you didn't know this, graphs are usually division bars. Most of the time we have time on the bottom because speed is distance divided by time. So if this was a speed graph, my distance would be up here and my time would be on the bottom because distance divided by time is speed. And so that's one of the ways, they don't always remind you of that on graphs, but graphs are a division bar, really. In this case, we'd be taking time of descent divided by wing length, but we're not actually doing a division here, but we're comparing the 2 pieces of data. And by the way, this experiment was by Hilary Dillner and Kathy Melville of Delaware Science Olympiad. This is where I got their information from. And then I put my own stuff in here as well. And so then we need to analyze the results. So we use that data, we graphed it. What is that going to tell us? So this is where you describe in words what is illustrated by your data found in the data tables and graphs. You describe the meaning of the results. You explain possible errors. So while individual trial results showed some variation, overall, as wing length increased from 5 to 9 centimeters, the average time of descent also increased from 4 to 8 seconds. This shows a direct correlation. Errors. So where could we have had some errors? Although the average results supported the hypothesis, the individual trials showed some variation. Some possible reasons for this could be due to air currents or the reaction time difference between the timer and the airplane dropper. All of those are possible errors that could come in. Causation, the action of causing something to happen. A correlation is a manipulated relationship between the connection between 2 or more things. In 9th grade, we'll talk about vaccine and causation and correlation. I could say that traffic accidents increase as we have more fruit imported from other countries, because I could have 2 graphs that say that my accidents are going up and my imported fruit are going up. But does one have an effect on the other? Well, no. It could be a correlation, but it's not a causation. Causation is I stuck my foot out and you fell over it. That's a causation. I caused you to trip. I stuck my foot out 20 feet away from you and you tripped. That's a correlation. I didn't cause it because I'm not the one physically tripping on you. Maybe you stubbed your own toe on the asphalt. I don't know. But one is causation. You cause something to happen. One is a correlation. So you have to be careful of those two. Just because there's a correlation doesn't mean there's a causation. So conclusion, why or why not your results support or did not support your hypothesis. So tell me, did it work or didn't it work? Include reasons why the hypothesis was supported or unsupported. Hypotheses are never wrong. Now that's an important part. They are either supported or unsupported. If it's an unsupported hypothesis, it means we need to change it. If it's a supported hypothesis, we need to make sure and do it again and again that we're getting the same results. So what are the practical applications for your result? What other questions could be asked from your conclusions? So the overall results of the hypothesis supported the hypothesis. A possible reason for this could be due to an increased surface area in the wing in contact with the air, allowing for greater air support. Recommendations for further explorations. So we're going to increase the time of descent due to bigger wing length. Suggests that increasing the wing length could lead to greater fuel efficiency. Other experiments could investigate changing wing shape or the change in the placement of the wing. And this is the point where I'm going to stop this part of the scientific method notes, and we're going to go on to this walk the plank. So if you need to, you can always look at this again, and or they are available online. But this is testable. The scientific method, you're going to need to know the order. Straight up, you need to know what is an independent and a dependent and a controlled variable. You need to know, when do I manipulate something? How many things should be manipulated? All of those things are important. Good testable questions, just so you know. All right, I will see you in the next set of notes or in class.